Hello and welcome to our Chapter 2 video. This is going to cover sections 2.3, 2.4, and 2.5. So we're starting section 2.3 and we're looking at some modern atomic theory and laws. Back in chapter 1 we defined what a law was, and these are the three main laws that support chemistry. So the first one is the law of conservation of mass, and we have looked at this one before, but now is our official definition. So it says in a chemical reaction, matter is neither created nor destroyed. So we're not going to magically make anything or magically get rid of anything. And we've talked about the importance of that when we balance chemical equations. In the second one, the law of definite proportions. So it says that all samples of a given compound, regardless of their source or how they were prepared, have the same proportions of their constituent elements. So that means that every time we have water, it's going to be H2O, 2 hydrogens for every 1 oxygen, and that doesn't change. The law of multiple proportions is a little bit different, but it sounds similar. It says when 2 elements form a compound, the ratios can be expressed as small whole number ratios. So really this is just saying that when we put hydrogen and oxygen together, they have to be in whole numbers. So H2O is water, H2O2 is hydrogen peroxide, and it's still following the law because we still have whole numbers. So we're going to do a couple practice problems to represent these. The first one says an automobile gas tank holds 21 kilograms of gasoline. When the gasoline burns, 84 kilograms of oxygen is consumed, and carbon dioxide and water are produced. What is the total combined mass of carbon dioxide and water that is produced? So we know that gasoline and oxygen are our reactants. They're what's going into the reaction. And carbon dioxide and water are produced. So we're looking for keywords. We have the word produced, we have the word consumed. So these are things that are telling us which side of the equation. So we can write out a little equation. Gasoline and oxygen are on the left, carbon dioxide and water on the right, and we know some of the numbers. We know we have 21 kilograms of gas, 84 kilograms of oxygen. We don't know how much carbon dioxide and water. That's what we're trying to find out. But because of the law of conservation of mass, we know that whatever these two are added together, it's going to be the same as these two added together. So just a little bit of math, we get 105 kilograms. 105 kilograms of carbon dioxide and water were formed. This tells us how much together. Not separately, that's a later chapter, but it tells us how much together. And this is the law of conservation of mass. So our second question, 2 samples of sodium chloride were decomposed into their constituent elements. One sample produced 6.98 grams of sodium and 10.7 grams of chlorine, and the other sample produced 11.2 grams of sodium and 17.3 grams of chlorine. Are these results consistent with the law of definite proportions? Explain your answer. So sometimes when we're given all of these numbers, it's good to rewrite them in a way that makes sense and just kind of takes out all the extra words. So sample 1, 6.98 grams of sodium, 10.7 grams of chlorine, and here's our sample 2 data. So it's just the same stuff that's written up here, just in a nicer format. Now the way to find out if this is consistent with the law of definite proportions is we have to make sure that it has a consistent ratio. So we do the chlorine to sodium ratio, which really just means we're dividing them. So it's the grams of chlorine divided by the grams of sodium, and we get a ratio of 1.5. If we do the same thing down here, so we're going to do 17.3 grams of chlorine divided by 11.2 grams of sodium, we also get 1.5. So yes, this is consistent with the law of definite proportions because the ratio stays the same. And there's the law it's connected to. Our third question, sulfur and fluorine form several different compounds including sulfur hexafluoride and sulfur tetrafluoride. Decomposition of a sample of sulfur hexafluoride produces 4.45 grams of fluorine and 1.25 grams of sulfur, while decomposition of a sample of sulfur tetrafluoride produces 4.43 grams of fluorine, 1.87 grams of sulfur for each sample, and show that these results are consistent with the law of multiple proportions. So the idea here is to show that there is a whole number ratio for each of these samples. They don't necessarily have to be the same, they just have to each have a whole number. So if we do the fluorine to sulfur ratio for the first one, we get a ratio of 3.56. If we do the ratio for the second one, we get a ratio of 2.37. So again, I'm just doing the mass of the fluorine divided by the mass of the sulfur for each one. And it doesn't matter which one you put on top of your division. I generally just pick whichever number is larger, so I end up with a whole number as opposed to just a decimal place. I want something larger than 1. Now when we compare these, we have a ratio of 3.56 and a ratio of 2.37. That means that the difference between these two is 1.5. Now those are representing the masses that are involved. If we look at the names of these compounds, sulfur hexafluoride and sulfur tetrafluoride, the prefixes here, hexa and tetra, tell us how many fluorines there are. So for each sulfur, there's only 1 because it doesn't have a prefix. But for fluorine, there's 6 fluorines. That's what hexa tells us. And here there's 4 fluorines. So we can also do an atom ratio, 6 to 4, and it's also a difference of 1.5. So we have a mass increase of 1.5 times bigger and a atom difference of 1.5 times bigger. So this is consistent with the law of multiple proportions because the amount that they have increased is the same that the amount of the mass has increased. Last one in this section, the ratio of sulfur to oxygen by mass in SO2 is 1 to 1. Find the ratio of sulfur to oxygen by mass in SO3. So the difference between SO2 and SO3 is just the number of oxygens. So the sulfur has stayed the same, but the oxygen increased. And if we look at how much the oxygen increased, it went from 2 to 3. So it increased by 1.5 times. 3 divided by 2 is 1.5. So that means that the mass ratio is going to increase proportionally. So the sulfur stayed the same, it will still be a 1, but the oxygen went up to 1.5. So we can say 1 to 1.5. A lot of times with ratios, we want to keep it a whole number. So if we multiply these both by 2, we'll turn them into whole numbers. So it would give us a 2 to 3 ratio. In the second question, it says, find the ratio of sulfur to oxygen by mass in S2O. So in this case, the sulfur has increased, but the oxygen actually decreased. So we're going to do each one independently. Oxygen, and we're comparing it back here to the original. Oxygen started at 2, and now it's down to 1. So it decreased by 0.5. And, oh, those are out of order. There we go. The sulfur increased from 1 to 2, so it increased by 2 times. So we're going to take these new numbers, the 0.5 and the 2, and that's our sulfur to oxygen ratio down here. And again, if we multiply everything in here by 2 to get them into whole numbers, it gives us a 4 to 1 ratio. And this is part of that law of multiple proportions. The law of multiple proportions is probably the trickiest one to understand. The big idea behind it is that it's always a whole number ratio, and we can track it or do math with it because the ratio can only increase by whole numbers. This only works because we're only adding 1 oxygen or 1 sulfur, not 1.2 oxygens or 0.8 sulfurs. It's going up by a whole amount. The last part in this section is Dalton's atomic theory. So Dalton's atomic theory is the first idea that led to our modern atomic theory. And so part of what we talk about with Dalton's atomic theory isn't actually true anymore. This is the way that it was written in the 1800s when Dalton figured it out. But since then, as we've talked about with laws and theories, there is room for improvement. And especially as technology changed, Dalton's atomic theory has changed with it. So we are learning it from the historical perspective, not necessarily the most accurate perspective. So for example, the first one says each element is composed of tiny indestructible particles called atoms. They're not indestructible. They have their own little pieces. So that is the first part, even though it's not completely true anymore. Number 2, all atoms of a given element have the same mass and other properties that distinguish them from the atoms of other elements. This really just means if you have a gold atom, it's a gold atom. Doesn't matter where it came from, it's the same as every other gold atom. Atoms combine in simple whole number ratios to form compounds. So this is very similar to the law of definite proportions. And number 4 says atoms of one element cannot change into atoms of another element. In a chemical reaction, atoms only change the way they are bound together with other atoms. So we can't turn lead into gold, is what this is saying. Now specifically this says in a chemical reaction. In nuclear reactions, atoms can change what type they are, and that's something that you will talk about in Chem 1B. So one more practice problem here. Which statements are inconsistent with Dalton's atomic theory as it was originally stated, and why? So the first one says all carbon atoms are identical. This is consistent. This is part 2 that says that all atoms of a certain type are the same. An oxygen atom combines with 1.5 hydrogen atoms to form a water molecule. This one is inconsistent because it's using a part of an atom. It's not combining whole numbers as part 3 said. 2 oxygen atoms combine with a carbon atom to form a carbon dioxide molecule. That is telling us what part 3 says. We're using whole numbers, we're combining atoms together. And lastly, the formation of a compound often involves the destruction of one or more atoms. This is not true. So this is also inconsistent because it's the opposite of part 4. The section 2.4 is looking at charges. So this kind of seems like it's off topic, but it's something that will be important in a later section. So we have 3 important properties here. The first one says that opposites attract. So the positive and the negative are going towards each other, there's an attraction. Same charges repel. So the positive and the positive are going away from each other, negative and negative are going away from each other. And the last one says that equal amounts of opposite charges cancel each other out. So one positive and one negative give us something that becomes neutral or no charge. The reason why we talk about this is because of the structure of the atom. So this is our last slide, and we're in section 2.5 now. And we're looking at the subatomic particles that make up an atom. Here is our very simple diagram of an atom. The center is called a nucleus. The nucleus is very small in volume, but very large in mass. It contains the protons and the neutrons. The protons have a positive charge. The neutrons are neutral. They each weigh the same though. They each weigh 1 mass unit. On the surrounding area, it's very large in volume, but very small in mass, and it contains the electrons. The electrons have a charge of -1, but they pretty much weigh nothing. We say they have a mass of 0. So, negative, no mass, positive, mass of 1, neutral, mass of 1. Overall, atoms have no charge. The number of electrons and the number of protons are the same. There are things that are charged. They have different names though. They're not called atoms, they're called ions, and we'll look at those in class. So here's our questions to go along with that. Which statements about subatomic particles are false? Protons and electrons have charges of the same magnitude but opposite signs. This is true. Protons are a positive one and electrons are a negative one. So same amount of charge, just opposite signs. Protons have about the same mass as a neutron. This is also true. They each weigh about 1 mass unit, or AMU. Some atoms don't have any protons. This is not true. In order for it to be an atom, it has to have at least 1 proton. And lastly, protons and neutrons have charges of the same magnitude but opposite signs. This is also false. Neutrons do not have a charge, they are neutral. Protons have a charge of a +1. Alright, that is it for our slides. We will talk about the rest of these sections in class. Thank you.